In this video, we're going to be talking about hypothesis testing using a single sample. Specifically, hypothesis tests for a population mean. So let's review the assumptions for a confidence interval for a population mean, because these assumptions are the same for a large sample hypothesis test for a population mean. First, that our sample mean is from a random sample. That the sample size n is large, meaning greater than or equal to 30, and that our sigma, the population standard deviation, is either known or unknown. This is the test statistic when sigma is known. The p-value is the area under the z-curve. This is the test statistic when sigma is unknown. Here, the p-value is under the t-curve with the degrees of freedom of n-1. The one-sample t-test for a population mean uses the null hypothesis that our mean equals the hypothesized value with our test statistic of t equals the sample mean minus the population mean divided by the standard deviation of our sample divided by the square root of our sample size. Our alternative hypothesis and its corresponding p-value, if our mu is greater than the hypothesized value, then our p-value is the area to the right of the calculated t with the degrees of freedom of n-1. If our mu is less than the hypothesized value, then our p-value is the area to the left of the calculated t-value with the degrees of freedom of n-1. And if our alternative hypothesis, we have that mu is not equal to the hypothesized value, then we'll have 2 times the area to the right of t, of a positive t, or 2 times the area to the left of t for a negative t. Our assumptions, that x bar and s are which are a sample mean and standard deviation sample from a random sample, that they come from a random sample. Second, that the population size n is large, meaning that n is greater than or equal to 30, or that the population distribution is at least approximately normal. Let's look at an example together. A study conducted by researchers at Pennsylvania State University investigated whether time perception, an indication of a person's ability to concentrate, is impaired during nicotine withdrawal. After a 24-hour smoking abstinence, 20 smokers were asked to estimate how much time had elapsed during a 45-second period. Researchers wanted to see whether smoking abstinence had a negative impact on time perception, causing elapsed time to be overestimated. Suppose the resulting data on perceived elapsed time in seconds were as follows. What is the mean and standard deviation of this sample? We should have a sample mean of 59.3 and a sample standard deviation of 9.84 with our sample size of 20. So now we'll state our hypotheses. So our null hypothesis is that the mean equals 45. So where mu is the true mean perceived elapsed time for smokers who have estimated or abstained from smoking for 24 hours. And our alternative hypothesis is that mu is greater than 45. Next, we'll verify our assumptions. It's reasonable to believe that the sample of smokers is representative of all smokers. And since the sample size is not at least 30, we must determine if it is plausible that the population distribution is approximately normal. To do this, we need to graph the data using a box plot or a normal probability plot. Now, since the box plot is approximately symmetrical, it's plausible that the population distribution is approximately normal. So now we'll compute the test statistic and the p-value. Plugging in our values, we'll get a test statistic of 6.50. Looking that up in our t-table, that's going to be approximately 0 for our p-value with an alpha of 0.05. So since our p-value is less than alpha, we reject our null hypothesis. and we state that there is convincing evidence that the mean perceived elapsed time is greater than the actual elapsed time of 45 seconds. So again, since our p-value was less than a, we rejected our null hypothesis with our alpha value of 0.05. So we're going to compute the appropriate confidence interval now. Now, since this is a one-tailed test, alpha is going to go in the upper tail, and 0.05 is going to go in the lower tail, leaving a 0.9 in the middle. So we're going to be developing a 90% confidence interval. Plugging in our values, that gives us an interval of 55.497 and 63.103. Notice that the hypothesized value of 45 is not in the 90% confidence interval, and that we rejected that null hypothesis. Let's look at another example. Here, a growing concern of employers is time spent in activities like surfing the internet and emailing friends during work hours. The San Luis Obispo Tribune summarized the findings of a large survey of workers in an article that ran under the headline, "Who goofs off more than 2 hours a day?" Most workers, survey says. Suppose that the CEO of a large company wants to determine whether the average amount of time of wasted time during an 8-hour day for employees of her company is less than the reported 120 minutes. Each person in a random sample of 10 employees was contacted and asked about daily wasted time at work. The resulting data are the following. What is the mean and the standard deviation of this sample? You should have gotten a sample mean of 116.8 and a sample standard deviation of 9.45 with our sample of 10 employees. So now let's state our hypotheses. Our null hypothesis is that mu is equal to 120, and our alternative hypothesis is that mu is less than 120, where mu is the true mean daily wasted time for employees of this company. Next, we'll verify our assumptions. The given sample was a random sample of employees, so we're good there. But since the sample size is not at least 30, we must determine if it's plausible that the population distribution is approximately normal. Using a box plot, it reveals some skewness, but there are no outliers. If a normal probability plot is done, it shows that the normality of this data is present. So therefore, we can move forward. So we'll now compute the test statistic and the p-value. So we'll plug our values in for t, giving us a t-value of -1.07, which we'll look up in our t-table, which gives us a p-value of 0.156 using our alpha of 0.05. Now, since our p-value is greater than alpha, we fail to reject the null hypothesis. There is not sufficient evidence to conclude that the mean daily wasted time for employees of this company is less than 120 minutes. What potential error could we have made here? That's right, a type 2 error. Let's do another example together. Abby and Raquel like to eat sub sandwiches. However, they notice that the length of the 6-inch sandwiches that they get at their favorite restaurant seems shorter than the advertised length. To investigate, they randomly selected 24 different times during the next month and ordered a 6-inch sub. Here are the actual lengths of each of the 24 sandwiches in inches. So we want to know, does this data provide convincing evidence at the alpha equals 0.1 level that the sandwiches at this restaurant are shorter than advertised on average? Then, given our conclusion in part A, what kind of mistake, meaning a type 1 or type 2 error, could we have made? And then explain what this mistake would mean in context. So we're going to use our state, plan, do, and conclude model. State. Well, we want to test the following hypotheses at the alpha equals 0.1 significance level. That our null hypothesis is that the mean equals 6, versus our alternative hypothesis that the mean is less than 6, where our mu is the true mean length of a 6-inch sub from this restaurant. Our plan. If conditions are met, we will perform a one-sample t-test for mu. Random. Our times were randomly selected to order a sub, so this should be a random sample of 6-inch subs from this restaurant. 10%. This restaurant is going to make more than 240 subs in a month, so we're okay there. As far as it being a normal or a large sample, the graphs don't show much skewness, and there are no outliers. So it's reasonable to use a t-procedure for this data, as we can see in our dot plot. Our do. The sample mean length is x bar for 5.68 inches with a standard deviation s of 0.66 inches. Now we find our test statistic, t. Plugging in our values gives us a t-value of negative 2.38. Next, we'll calculate our p-value. So using the t-distribution with a 24 minus 1, so a 23 degrees of freedom, the p-value is between 0.01 and 0.02, so approximately 0.0130. Now we can conclude. So because the p-value of 0.0130 is less than our alpha of 0.1, we reject the null hypothesis. There is convincing evidence that the true mean length of 6-inch subs at this restaurant is less than 6 inches. Now, because we rejected the null hypothesis, it's possible that we made a type 1 error. So in other words, it's possible that we found convincing evidence that the mean length was less than 6 inches, when in reality the mean length is 6 inches.